Okay, so what was the last we have covered? Electric field intensity, I think, right? Electric field intensity at a point due to point charge, and we have written the formula for electric field intensity at a point due to a point charge, 1 upon 4 pi epsilon naught into q by r square, which I can also write as kq upon r square, right? So this was the formula for electric field intensity at a point due to a point charge or source charge. And couple of days back we have discussed about a principle called superposition principle. Superposition principle. Superposition principle. Right? If you remember, I told you that superposition principle is a two-body interaction. It is a two-body interaction. Especially it is a two-body interaction. It is a two-body interaction. Okay, two-body interaction. So as I said, it is a two-body interaction. If I have more than two charges, or if I have more than two bodies which have different charges, in that case what we'll do? See, for example, I have a charge q1, I have another charge q2, I have another charge q3, another charge like q4. Like this, I have n number of charges qn. So each charge will interact with a test charge separately. Now here, if I place a test charge q naught somewhere in between these two, charges, from q1 to q naught, I will take the distance as r1. From q1 to q naught, I will take the distance as r1. q2 to q naught, I'll take the distance as r2. q3 to q naught, I'll take the distance as r3. From q4 to q naught, distance I'll take as r4, and from qn to q naught, I'll take the distance as rn. Right? So how this q1 exerts a force on q naught? See, when I talk about q1, remaining charges I am not considering at all. When I talk about q1, remaining charges, whether they are present or absent, I am not bothered about the other charges. I am interested only about these two charges. q1, what it will do to q0. Both are positive charges. When both are positive charges, what happens to the force? q1 repels q0 or not? q1 repels q0. Let me take this as F1. What is F1 here? F1 is the electrostatic force between q1 and q0. Both are separated by r1. Now what this q2 will do? q2 also repels q0 because both are positive charges. Let me represent that force as F2. What is this F2? Electric force between the charges q2 and q0, and the separation between them is r2. Similarly, can you tell which force will act between q3 and q0? That force I'll represent as F3. What is this F3 represents? F3 is the force of repulsion between q3 and q0. Similarly, if I take q4 on q0, q4 on q0, that force I will take as F4. What is this F4? F4 is the force of repulsion between q4 and q0 separated by distance r4. And lastly, qn also repels this q0 and let me take this force as Fn. Now what is the total force acting on Q naught due to the remaining source charges? Total force I want. See, F1 is what? F1 is the force of repulsion between Q1 and Q naught. F2 is the force of repulsion between Q2 and Q naught. Similarly, F3 is the force of repulsion between Q3 and Q naught. F4 is the force of repulsion between Q4 and Q naught. And finally, Fn is the force of repulsion between Q1 and Q naught. Now, what is the net force? Net force on which charge? On Q naught due to remaining charges, due to the source charges. What are those source charges? Q1, Q2, Q3, so on, Qn. How can I write? Net force means what? Summation. So F1 is the force due to Q1 plus F2 is the force due to Q2 and F3 is the force due to Q3 plus so on, finally Fn. Already we have written this in the last class, right? I mean a couple of days back. Now what is the formula for force? What is the formula for force? General formula. F electrostatic force is equal to K Q1 Q2 upon R square is the general formula. I'll apply this formula to each one of the forces. Therefore, what is the value of F1? What is the value of F1? Okay, I'm writing magnitude. Let me write magnitude only. F1 is what? F1. How can I write? K into F1 is the force between which two charges? F1 is the force between Q1 and Q naught. So here I'll write one as Q1, other one as Q naught divided by R1 square. What is F2? K Q2 Q naught by R2 square. Similarly, F3 if I write, F3 is equal to K Q3 Q naught by R3 square. So on. If I write the formula for Fn, I can write this one as K Qn into Q naught by Rn square. This is how we write. Now what is F net? How can I write the magnitude? Magnitude means what? Magnitude of this force can be written in modulus. F net modulus I can write as F1 bar plus F2 bar plus another force F3 bar plus so on plus finally Fn bar. Now when I remove modulus, how can I write? I can write directly, I won't put bar now. Simply I'll write F net is equal to F1 plus F2 plus F3 plus so on plus Fn. This is the force. Till here we have written that time. Now what we want? We want electric field intensities. What is the formula for force? In place of F1, what can I write? In place of F1, I can write K Q1 Q naught upon R1 square. F2 is nothing but K Q2 Q naught upon R2 square plus K Q3 Q naught upon R3 square plus so on plus K Qn into Q naught by Rn square. And here in place of F net, K Q net, that is net charge, into Q naught by resultant of that force R square, right? R square. Okay. Can I cancel anything? Can I cancel the terms on both sides? If at all, if I cancel, what are the terms that I can cancel on both sides? I can cancel, okay, let me cancel Q naught. Let me put K here. Q naught gets cancelled in all the terms. Q naught, I won't cancel K. The reason I won't cancel K because what is the formula you have for KQ by R square? What is the formula that you have for KQ by R square? Just now I have written. Electric. KQ by R square is nothing but electric field intensity. Now here what can I write? KQ net by R square gives what? This is nothing but E net is equal to KQ1 by R1 square I can write as E1. KQ2 by R2 square I can write as E2 plus another one E3 plus so on plus En. So this is also obeying principle of superposition. As force obeys principle of superposition, electric field intensity also obeys the principle of superposition. Important. So this I have written for discrete charges. All are separate charges, individual charges. Individual charges. Individual charges, right? Principle of superposition I can write in magnitude. Okay, so E net is equal to E1 plus E2 plus E3 plus so on plus En. This is the formula that I have written in magnitude. In magnitude. If I want to write this in vector form, how can I write? You remember about unit vector? I have to multiply this magnitude with a unit vector so that I can get given vector. I can get a given vector. If I multiply this E net with unit vector or K into Q naught by R square with unit vector, then I will get given vector. So how can I write E net bar as? Now what I will do is in vector form, let me take this equation. What is remaining? KQ net by R square. If I multiply this term with R cap, then it becomes what? A vector form is equal to, same here also, KQ1 by R1 square. Here I can write R1 cap plus KQ2 by R2 square into R2 cap plus so on plus KQN by Rn square into Rn cap. If I multiply with a unit vector, then what I'll get? I will get a given vector. I'll get a given vector. If I multiply the magnitude with the unit vector, I think in the last class I told you about unit vector. If you remember, n cap is equal to what? Given vector by its magnitude. Magnitude I can write simply as A. Now if I bring this A to the left side, A bar can be written as what? A bar can be written as A into n cap. So this given vector is nothing but the magnitude of this given vector multiplied by unit vector. So if I multiply with the unit vector to this magnitude, what I will get? I'll get a vector quantity. So I can write this one as E net bar is equal to this one as E1 bar plus E2 bar plus E3 bar. This is in vector form, plus so on plus En bar. So this is the principle of superposition in vector form. This is the principle of superposition in vector form. In vector form. So this is how we write in vector form. In vector form, in terms of which vector? In terms of unit vector. That this I have written in terms of unit vector. This I have written in terms of unit vector. In terms of unit vector. Unit vector. Now what is the formula for unit vector? What is the formula for unit vector? Unit vector is nothing but general formula is what? Given vector by its magnitude. So can I write R1 cap as R1 cap as, how can I write? R1 cap in place of n cap. If I write R1 cap, what is A bar given vector? E1 bar, that is KQ1 by R1 square. So R1 cap I can write as R1 bar by R1. So can I write like this? I'll show you. Based on this, if I write R1 cap is nothing but R1 bar divided by magnitude of this R1. Magnitude of this given vector is R1, right? So what about R2 cap? R2 bar divided by R2. Similarly, if I write Rn cap, if I write Rn cap, how can I write? Rn bar divided by Rn. So this I can also write in terms of given vector as, okay, right? This I can write as or E net, okay, let me write this one. I'll show you this one. So how can I write this one? K Q net by R square into, how can I write R cap as? R bar by modulus of R bar is nothing but R, is equal to E1 bar, that is K Q1 by R1 square into R1 cap I can write as R1 bar by R1 plus KQ2 by R2 square into R2 bar by R2 plus so on. Finally, KQN by Rn square into Rn bar divided by Rn. On further simplification, how can I write this? Now R square into R is R cube. So this I can write as K Q1 by R cube into R bar is equal to K Q1 by R1 cube into R1 bar plus K Q2 by R2 cube into R2 bar plus so on plus KQN by Rn cube into Rn bar. So this is also a vector form, but in terms of given vector. This is also the formula for principle of superposition in vector form, but this is in terms of given vector. This is also the formula for principle of superposition in vector form. In vector form, in terms of in terms of given vector, right? This is how we can write, and this is nothing but E bar only, E net bar. E net bar is equal to E1 bar plus E2 bar plus so on plus En bar. Same thing I can write here also. This one I can write this one as E net bar is equal to E1 bar plus E2 bar plus so on plus En bar. En bar. So this is about the principle of superposition of charges, or simply principle of superposition. I can apply this principle of superposition for forces, and also I can apply this principle of superposition for electric field intensity. Especially this is applicable for vectors. This principle of superposition always is applicable for vectors. Vectors, important. Okay. Now let me give you another concept called continuous distribution of charges. Till now we have discussed about discrete charges. Discrete means what? Separate. Discrete means what? Separate. See here, what I did is I have taken different charges. In this example, Q1 is separate charge, individual charge. Q2 is individual charge. Q3 is individual charge. All I have taken point charges separately, right? Point charges. For example, if I give you a thin rod, how can you express the charge in that case? See, for example, I have given a thin rod or thin wire. This is a thin wire. Its area of cross section is very, very small when compared to its length. It has only length. If I give a charge plus Q to this thin wire, right, how this charge will spread? This charge spreads throughout this thin wire. This charge spreads throughout this thin wire. How it spreads? Let me take plus. Let me show you with another color. Plus. It is not selected. So plus like this. Which charge it got spread? This plus Q. If I consider a thin rod, thin wire, this total Q plus Q I have given to this thin wire, so it got distributed throughout this length of the wire. So this, if I add up all the charges, how much I should get? Plus Q. If I add up all these charges, I will get this plus Q. For how much length? L length. So for L length, what is the charge that I have given? Plus Q. So I can write like this. For L meter length, what is the charge that got distributed? Q coulomb of charge. Now what I want is, for 1 meter length, how much charge it will take? 1 meter, unitary method, 1 meter length, how many coulombs this 1 meter will take? How will you do? Yeah, 1 into Q by L. 1 into Q by L. 1 into Q by L. I can write this one as Q by L. This ratio, charge per unit length, is called as linear charge density denoted by lambda. What is this lambda called? Linear charge density. Linear charge density. Remember this. Linear charge density is defined as, how can you define? Charge per unit length. Charge per unit length is called as linear charge density. And these will come under the topic called continuous charge distribution. Continuous charge distribution. Continuous charge distribution. Okay, continuous charge distribution. That means charge got distributed continuously throughout this wire. Throughout this wire. Charge got distributed continuously throughout this wire. And this is this one dimensional or two dimensional or three dimensional? This geometry will belong to 1D or 2D or 3D? I am considering only length, right? Length. So length means what? Only length you have. You don't have, for example, if I give you a square, what can you find out? Length as well as breadth. So what you can find out? Area. This is 2D. This is 1D. If I consider a sphere, 3D, or cube, 3D, right? So this is first one. What is first one? 1D. First one is 1D. That 1D we have defined a quantity called linear charge density. For 1D we have defined linear charge density. So let me take this as first one. First one, 1D. For 1D I have defined linear charge density. For 1D I have defined a linear charge density because it has only length. You don't have any area of cross section. Area of cross section is negligible with respect to length. Area of cross section is negligible with respect to length. Length is very big when compared to area. Right? Now what are the units? Immediately, the moment you got the physical quantity, new physical quantity, I need units and dimensions. Units and dimensions. Now what is the formula for linear charge density? Linear charge density, lambda formula is Q by L. Now can you tell me, based on this formula, what are the units in SI system and what are the dimensions? SI unit of lambda. What are the units of charge? Coulomb. What are the units of length? Meter. Everything here only I have written. Coulomb and meter. So Coulomb per meter, meter I will take to the numerator. So this is how we write the unit. Make a habit of writing units with powers. Don't write a Coulomb per meter. This is wrong way of representation. Even in some books it will be given like this, but this is wrong way of representation. Per meter. Coulomb per meter. Coulomb per meter. Right? Now what is the dimensional formula of this lambda? Dimensional formula of lambda. Dimensional formula of lambda. Dimensional formula of lambda. Charge. This is not a fundamental quantity, right? So how can I express this Q in terms of fundamental quantity? What is the formula for current? Current I is equal to charge by time, rate of flow of charge. So from this, what is the value of Q? IT. Current is a fundamental quantity. Time is a fundamental quantity. Now what is the dimensional formula of this Q? AT. So I can write here AT. I can write this one as AT divided by L. AT divided by L. So I'll take this L to the numerator. It becomes L to the power minus 1, T to the power 1, A to the power 1. Or in this, I don't have mass. So can I write like this? M to the power 0, L to the power minus 1, T to the power 1, A to the power 1, like this. See, in books, like sometimes you may not expect the powers of 1 because T to the power 1 is nothing but T only. So T only. I am writing T to the power 1 and A to the power 1. So this is how we write dimensional formula. Whenever you get a new physical quantity, try to write their units as well as dimensional formulas. Dimensional formula of lambda. Chalo, second one. What is second one? 2D. In 2D, let me take a square or disc or ring. Second one. What is second one? 2D. In 2D, I'll take an example of a square plate. A square plate. Let us assume that this is a plate. Or I can take a disc. Or I can take a circular disc, right? Circular disc. Or I can take a ring. All these belong to 2 dimensions. This is a ring, circular ring, circular ring, circular disc, square plate, right? Now for these, if I give a charge Q to all these plus Q, what happens? This Q has to spread out the given diagram. So if for this square plate, plus gets distributed uniformly throughout this square plate. Throughout this square plate. That plus Q charge gets distributed throughout this square plate. That is called as continuous distribution of charge. In this disc also, the charge plus Q got spread throughout this. If I take this as a disc, this charge gets distributed uniformly throughout this disc. Now in case of circular ring, in this only you have material, you don't have, this is hollow, right? So this charge gets distributed throughout this ring only, not within the ring, not inside, because this is the this is where you have material. Wherever you have material, the charge gets distributed. So this is how the charge gets distributed throughout. So this is the case of 2D. Now can I ask you what is the area of square? Do you have any area? Yes. If I take side as A into A is A square. What is the area of this disc? It is circular. What is the area of circle? Area of circle is pi r square. This is also in the form of a circle. So what is the area? Pi r square. So then what should be, okay, now this area got, I mean this charge got spread out throughout this area. That means I can write like this: a meter square got distributed by how much charge? Q coulombs of charge. So this Q coulombs of charge got distributed throughout this area A. So for 1 meter square, what is the charge that gets distributed? For 1 meter square. Yeah, so for 1 meter square, what is the charge that gets distributed? How much coulomb? How many coulombs it gets distributed? So answer is Q by A. So 1 into the charge that is given to the square plate or disc or ring by area, I can write as Q by A, and this Q by A is denoted by symbol sigma. This sigma is called as, so it has surface, right? It has surface, this has surface, this also has surface. So what is this charge density called? This is called as surface charge density. So what is this called? Surface charge density. Surface charge density. This is how we write. Important. So this is a continuous distribution of charge. All these three, 1D, 2D, 3D, all these will come under continuous distribution of charge. Continuous distribution of charge. So I got one more physical quantity, sigma. So what is it called? Surface charge density formula is surface charge density sigma is equal to Q by A. So based on this formula, can you write down the SI unit and also the dimensional formula for this? What is the SI unit? For charge it is coulomb. For area it is meter square or square meter. So answer, SI unit is coulomb per meter square. So SI unit of sigma is nothing but coulomb per meter square. I am writing in the numerator itself. Meter square I have taken to the numerator, I have written coulomb per meter square. Okay, let me put dot because you feel as if you take that as centimeter. Coulomb into meter to the power minus 2. Coulomb into meter to the power minus 2. Right, Q by A. Now what is the other one? What is the other one? Dimensional formula I need to write. So dimensional formula of this sigma. Dimensional formula of this sigma. Dimensional formula. What is the formula that we have? Charge per unit area. What is the dimensional formula for charge you have written? AT. Right? AT will not change because AT is the dimensional formula of charge. By area means what? Area. Meter square. Meter is the unit of length. So meter into meter. Meter means length. Length into length. L square. So this formula I can write as L to the power minus 2 T to the power 1 A to the power 1, or I can also express this in terms of mass, M to the power 0 L to the power minus 2 T to the power 1 A to the power 1. Right. Third one is sphere or cube, whatever, 3-dimensional. Cone, right? Cone is also 3D. Cone belongs to 3D. Cube belongs to 3D. Cuboid belongs to 3D. Sphere belongs to 3D. Right? Third one is 3-dimensional. I can take sphere. Assume that this is a sphere. This is a sphere, like it's just like a football or globe. Imagine a globe or imagine a sphere. And this sphere you have both like conducting and non-conducting. This we'll discuss later on. But here let me write here itself. Conducting sphere I can take, non-conducting sphere. This I'll explain later on when I discuss about Gauss law. Here sphere can be taken as conducting sphere, and one more is non-conducting sphere. Because we have only sphere in our syllabus. Right? Sphere, conducting and non-conducting, both are there in our syllabus. Conducting and non-conducting. One more 3D you can give a cube. Right? Cube, let me take a cube like this. This is a cube. All sides are same. So 3D, it has a volume. What is the volume of sphere? Volume of sphere is 4 by 3 pi r cube, provided if r is the radius of sphere. What is the volume of a cube? If I take side as A, each side as A, then volume of a cube is how much? A cube. A cube. So here you have volume. Here you have volume. And if I take cylinder, cylinder is also a 3D. If I take cylinder, what is the volume of cylinder? If I take a cylinder like this, what is the volume of cylinder? Right, volume of cylinder is, if I take its length as L, what is the area of circle? Area of circle A is equal to pi r square. Okay, let me write R, capital R, R square. Now if I take R as radius of this, then area of circle is how much? Pi r square. How to find out volume? What is the formula for volume? Area into length. What is the value of area? Pi r square into L. So this is the formula for volume. Volume of cylinder is nothing but area into length. The general formula for volume of any 3D is volume is nothing but area into length. Area into length. Okay, but here you don't have any length. Sphere, for sphere you have only radius. So 4 by 3 pi r cube. Area into length. So here also area into length. I can find out area of this square. What is area of square? Just now we have written. We don't write it, right? A into A gives area of square. Area of square multiplied by this width or length. A into A into A. How much you'll get? A cube. This is how we write. So these are the three-dimensional figures. Three-dimensional figures. Mostly we have cylinder, cube, and also we have sphere mostly. And sphere, for time being, just note it down. Conducting and non-conducting. We'll discuss this later on. Conducting and non-conducting. Conducting and non-conducting. Right. This is about now. If I give a charge to all these plus q. Okay, let me show you what is the difference between this conducting and non-conducting here itself. See, for conducting, conductor is like a football. Okay, imagine a rubber ball. In rubber ball, inside, is it filled with stuff or is it empty? If I take a rubber ball, is it filled with some stuff or is it empty, hollow? Hollow. Conducting, remember, conducting is nothing but hollow. Hollow sphere. Hollow sphere is always conducting, hollow. Just like imagine a globe. Normal globe, I mean, you can find these globes in schools, right? When you have studied about social studies, they will show you this globe, right? In globe, nothing will be there. It is completely empty. I mean, inside that will be empty. That is called as hollow. When nothing is there, if I give plus q charge here to this hollow sphere, where this charge q should get distributed? Yeah, only on the surface of the sphere. The charge gets distributed throughout continuously throughout the sphere on the surface of sphere. This is in case of hollow sphere. This is in case of hollow sphere. If I take non-conducting, this is in case of a conducting. This is in case of, for conducting sphere, charge gets distributed on the surface of sphere. Radius of sphere is r. For non-conducting, imagine like which is filled with some stuff. Inside it is filled with some stuff like cork ball, right? Cork ball or tennis ball. Inside there is that is filled with some stuff. So when it is filled, it's like just like samosa. Imagine, so samosa or sandwich, it is filled with what? Some stuff. So in this case, In this case, this is called as non-conducting sphere. Non-conducting sphere. This charge gets distributed inside the sphere completely because it is filled with stuff. Filled with some stuff. That is called as non-conducting sphere. In case of non-conducting sphere, where you can expect the charge? Inside this stuff, this charge gets distributed throughout. In case of conducting sphere, charge gets distributed on the surface. This is the difference between conducting and non-conducting. More we'll discuss when we talk about Gauss law. There we have applications. So for time being, just make a note of it. Conducting means what? It should be hollow. Non-conducting means what? It should be filled with some stuff. Right? So this is about hollow sphere and a non-conducting sphere, which is called as a non-conducting sphere. The charge gets distributed completely inside the sphere. You can ask, can I give negative charge? Yes, I can give. If I give minus q here, what is the charge that gets distributed? Minus q. Minus q is distributed throughout with minus sign only. Here also, if I give minus q, this plus I'll replace with minus. But basically, if I do not mention anything about charge, which charge you have to take? Always positive. Remember, always positive. So this is about 3D. Now, how much volume this has occupied? How much volume? So how much? Okay, what is the formula for? For all these cases, you have volume, right? So volume V meter cube will take how much charge? V meter cube has taken, how much charge? Q coulombs. So Q coulomb of charge is taken by V meter cube of the material. So for 1 meter cube, how much charge, how many coulombs it will take? So the answer is 1 into Q by V. 1 into Q by V, this is nothing but a charge per unit volume. This I will represent with rho. What is this rho called? Here what we have taken? Volume. So that is what it is called as. This is called as volume charge density. Volume charge density. Now you have got another physical quantity, new physical quantity, volume charge density. Now you write down the SI unit and dimensional formula. Volume charge density V. Volume charge density is rho, right? Volume charge density is rho, right? Volume charge density rho. So rho is equal to charge per unit volume. This is called as volume charge density. Now in this case, if I ask you the SI unit coulomb per meter cube. So SI unit will be SI unit of rho is nothing but coulomb per meter cube. Coulomb into m to the power minus 3. And the dimensional formula of rho is nothing but AT. This is for charge. Volume is nothing but L cube, meter into meter into meter. So I can write this one as L to the power minus 3, T to the power 1, A to the power 1. Or if I want to express this in terms of mass also, mass is not there, m to the power 0, L to the power minus 3, T to the power 1, A to the power minus 1. This is how we write the dimensional formula. Dimensional formula of rho. Dimensional formula of rho. So we have discussed 3 types of continuous charge distribution. What are those 3 types? One is linear charge density, surface charge density, and the third one is volume charge density. Volume charge density. Okay, now especially for MPC students, you have a concept of, mainly you can expect differentiation and integration, right? So I can also write, let me write like this. Lambda is always constant, remember. What is lambda? Linear charge density. Linear charge density lambda is nothing but a total charge by total length. Now if let me consider again, for this thin wire, if I consider a small elemental length dl, this is what dl, this is a small elemental length. What is this dl called? Small elemental length, or I can say infinitesimal length, means very small. For this elemental length, a small elemental length, how much charge it will take? Because I have written in terms of differentiation. So for this elemental length, dq is the charge. So in place of u I can write dq. In place of L I have to write dl. This is how we write. This ratio always remains constant. This ratio always remains constant. This is for linear charge density. And if I ask you to write for small elemental area, what will be the charge? dq. So what will be the formula for sigma? What will be the formula for a surface charge density or areal charge density? Yeah, dq by dA, that's it. So here if I write surface charge density sigma is equal to Q by A is the general formula. If I consider total area A, for the total area what is the total charge? Q. But now I am considering small elemental area for dA elemental area, so dq is the charge, small amount of charge. This is for, this ratio always remains constant. This ratio always remains constant. Similarly, I can also write for volume charge density. Similarly, I can also write for volume charge density. Volume charge density, rho is equal to charge per unit volume. I can also write dq for the small amount of charge for how much volume? Elemental volume dV. This ratio always remains constant. This ratio always remains constant. Remember this. Right? So basically we'll write like this. From this, what is the value of dq? How can I write a dq from this? I can write a dq as lambda into dl. I can write this one as lambda into dl. Now from this I can write a dq as sigma into dA. From this I can write dq as rho into dV. This is how we write. We'll discuss more about these formulas while discussing about Gauss law. While discussing Gauss law. For time being, just note the formulas. If I ask you for dq, small amount of charge, dq is equal to lambda into dl. For sigma it is, right? So I can also write like this. I can also write like this. See, dq is equal to what is lambda? Q by L into dl. From this I can write dq as q by A into dA. From this I can write dq as q by V into dV. Right? Don't cancel L and L here. Right? A and A don't cancel like that, because dV is separate and V is separate. dl is the single term, L is a single term. Don't cancel L and L there. That is not a d into L. dl is a separate term. Okay. So this is how we write. Okay. Right. Okay, fine. Now, so this is about the charge densities. We have three types of charge densities: linear charge density, surface charge density, and volume charge density. These will come under continuous distribution of charges. Continuous distribution of charges. Okay. Now let me take another concept. Okay, now tell me. Let me give you a few questions based on electric field. Let me give you question like this. I'm giving you an equilateral triangle. Equilateral triangle means, you know, all sides are equal. Let me take A as the side of a triangle. Right, let me represent these sides as A, corners as A, B and C, and I have placed the charges, identical charges plus Q at all the corners of a triangle, equilateral triangle A, B and C. Right. So here I have placed a charge plus Q, here I have placed a charge plus Q, here also I have placed a charge plus Q. All these are discrete, right? These are separate charges. Now what I want is, I want the electric field intensity at the point of intersection of these charges. Point of intersection. Where can you expect point of intersection from the corners? What is this line in mathematics called? If I draw a line like this, what is this line called? Especially you have one name, median. What is that called? Median. So all these medians, if I join, they will meet at a point. They will meet at a point. Now where I want the electric field intensity? Electric field intensity at the point of intersection of the medians. Question is, find the magnitude of electric field intensity, magnitude of electric field intensity at the point of intersection of the medians as shown in the figure, as shown in the diagram, as shown in the diagram or figure. So how to approach this problem? Always remember, wherever intensity of electric field is asked, there you have to imagine what? wherever intensity of electric field is asked, there you have to imagine a small positive test charge. So here at this point, imagine a small positive test charge. Small positive test charge. Small positive test charge Q naught. So wherever intensity of electric field has been asked, there you have to imagine a small positive test charge. Now from point A on Q naught, what is the direction of force? At point A, what is the charge I have taken? Plus Q. What is there at the point of intersection? Plus Q naught. So is there any force of attraction or repulsion? Repulsion. So A will repel in this direction. So let me take this as force. Okay, let me take this point as O. Force on O due to which point? A. Now on O due to B. On O due to B. What is the direction of force? What is the direction of force? On O due to B. Q repels Q naught or attracts? Repels. So in this direction it will repel. So this is the force on O due to B. So this is the direction. This is the direction. Similarly, in what about C will do? C will repel point O or C will attract point O? C will also repel. So in which direction it will repel? Like this it will repel. So this is what force on O due to point C. Force on O due to point C. Now if I show you this pink color arrows, if I show you the pink color arrows separately like this. Okay, let me represent with pink color only. I am showing you separately. How are these three? These three are from the common point. This one is FOC, this one is FOB, and this one is FOA. Right? So this is in the form of Y shape. Now what is the resultant of FOC and FOB? These two vectors are like this. There is certain angle, right? There is certain angle. Are these forces equal or not? Why? Why they are equal? What about this length? This length and this length, are they same or different? Same. When the distance is same, force will be same. Force will be same. If I take the angle between them as theta, according to parallelogram law of vector addition, what is the formula that we have for magnitude of resultant? Magnitude of resultant. See, let me take this as F. This one is also F. This one is also as F. Why? Because forces are same. Because distances are same. Now, when forces are same, resultant force, how it will act? See, just imagine the figure like this. If you remember this parallelogram law of vectors, if I take this as P bar, this one as Q bar, and if theta is the angle between them, resultant always lies between these two vectors. So where can I expect the resultant of these two vectors? Exactly in between them. And forces are same, right? When forces are same, how can I expect the resultant? Resultant force exactly bisects this. This is the resultant force. Let me take this as F dash. What is F dash? F dash is the resultant force of which two forces? F dash is the resultant force of FOB bar FOB bar and FOC bar. FOB bar and FOC bar. Now what is the formula for magnitude of F dash? What is the formula that we have for magnitude of resultant? What should I write here? F dash is equal to root over F square plus 2F into F is F square again into angle between the two vectors is how much? Theta, cos theta. Angle between them is cos theta. Okay, so that is the resultant. Now remember here the charges are not moving. That means all at this point net force is how much? Under equilibrium, what is the condition? Because all the forces are equal, right? When all the forces are equal at this point, what is the net force? 0. Net force should be 0. Now what is this F dash you have taken? F dash is the resultant force of what? FOC and FOB you got like this. Now how is this F dash with this F? What is the angle between them? 180. Angle between them is 180 degrees. Now this point is in equilibrium. So what is the net force now? 0. Answer should be 0. There is no question of doing any mathematics here. Right? When at this point under equilibrium, this is the point where net force due to all these forces is 0. So nothing to do. No need to apply any mathematics here. Directly, what is the resultant force of these two? FOA, FOB and FOC, F bar, F dash. How is this F dash with F? Exactly opposite in direction. That is the reason this point is remaining there itself. So under equilibrium, what is the net force now? I can write like this. Under equilibrium, net force on which point? At point O, where which charge you have taken? Net force on point O or at point O. I can write this one as 0. When net force is 0, what? But I am not asking force here. What I am asking? I am asking electric field intensity. Electric field intensity at point O. Electric field intensity at point O. Now, if net force is 0, I have written this is in vector form. How can I write the magnitude? Simply F net. F net is also equal to 0. I will remove this bar. If I remove this bar, what is this indicates? Magnitude of force. Magnitude of force at point O is 0. When force itself is 0, what is the value of electric field intensity? What is the formula that we have for electric field intensity? General formula. General formula for E is equal to F by Q naught. So this is nothing but F net by Q naught. What is F net you got? 0. So net electric field at point O is also 0. Net electric field at point O is also 0. So this is under equilibrium. Under equilibrium, net force at point O must be 0 because charge is not moving anywhere. Charge Q naught remains there itself at point O. That means I can say that net force on the charge Q naught is said to be 0. Net force on the charge Q naught is said to be 0. Okay. Net force on the charge Q naught is said to be 0. Now you tell me, let me give you a bigger one. Try to do this. Question number 2, last one for today. Question number 2. I'll ask you. Okay, I'm giving you a regular hexagon. Means what? Hexagon means how many sides? 6 sides. Hexagon, regular hexagon, regular hexagon. I'll show you the diagram. Let me show you the diagram. Diagram looks like this. This is the regular hexagon, means all sides are same. All sides are same. At the corners of this regular hexagon, I have placed identical charges at a different points. Let me take this point as A, B, C, D, E and F. Side of each hexagon is A and A. Now I want the magnitude of electric field intensity at the point of intersection of the diagonals. Now, which two corners I can join? I can join BE, I can join AD, I can join this FC. I can join this. This is moving. Let me draw like this. Okay, this is how you have. Okay, so this is how you have. So what I'm asking, I am interested to find the magnitude of electric field intensity at the point of intersection of the diagonals. So what I have to assume there? At the point of intersection, what I have to assume? Small positive test charge. Let me take this point as O, this point as O, this point as O, and all charges are identical. At point A you have plus Q charge, at point B you have plus Q charge, at point C you have plus Q charge, at point D also you have plus Q charge, at point E you have plus Q charge, at point F also you have plus Q charge. At point O we have to imagine a small positive test charge. Small positive test charge. Small positive test charge. Now what I am interested? I am interested to find the magnitude of electric field intensity at the point of intersection of diagonals. Point of intersection of diagonals for a regular hexagon. As shown in the figure. As shown. Find the magnitude of electric field intensity E bar at the point of intersection of diagonals for a regular hexagon as shown. Now, if I take AD diagonal, at point A what you have? Plus Q. At point O you have plus Q naught. So what this plus Q will do on Q naught? What this plus Q will do on Q naught? It will repel. So in this direction you have Let me, acha, one more thing. What about all these remaining sides? See, this is an equilateral triangle, this is an equilateral triangle, this is an equilateral triangle. So all sides are, in case of regular hexagon, all sides are equal. Okay, already I have written there. A, here this is, okay, this is A, this one is also A. Right? So all these are equilateral triangles. Okay, equilateral triangles. Now this side is A, so this has repelled. So in this direction force is there. When in which direction electric field will be there? Electric field intensity always acts in the direction of force. So I can say that this is the direction of electric field. So this is the direction of electric field, E on O due to A. This is like this. Now what this D will do? Point D, at point D you have plus Q, and here at point O plus Q naught is there. So D on O, what is the direction? Direction of electric field should be in this direction. So this is what? Electric field on point O due to D. How are these two? Are they equal in magnitude? Yes. Distance is same. Are they equal in magnitude? Yes, they are equal in magnitude. What about directions? Opposite. So they get cancelled. They get cancelled. Note, so net electric field along the horizontal line is 0. Now let us see one more line. BE, B on O. B on O. At point B Q, at point O Q naught. Q repels Q naught. This is the direction. So I can write this one as electric field on O due to B. Now similarly, E will repel O. That is E at E point E you have plus Q. At point O you have plus Q naught. This will also repel. So let me write this one as E on O due to E. Due to E. How are these two? Opposite but equal in magnitude. So these two also get cancelled. These two also get cancelled. So net electric field along this line is also 0. Now we have one more line left. CF. C on O. This is the electric field intensity on point O due to C bar. Due to C. Similarly, F on O. How are these two? Electric field intensity on O due to F. These two fields are also equal in magnitude but opposite in direction. So what is the net electric field at point O? 0. So no need to calculate. All get cancelled. All get cancelled. So simply I can write net electric field at the point of intersection of the diagonals at point O is equal to 0 under equilibrium. Under equilibrium. Remember this. Under equilibrium. Now for you I'll give you one question. Try this at home. Try this at home. This is the question. Now let me give you a diagram like this. Question is same. Question is same. I'm just drawing the diagram. Drawing the diagram. This is second bit. You try at home. Second bit. Try at home. So this is the diagram. This is also a regular hexagon. This is also a regular hexagon. Regular hexagon. Right, let me take this point again as A, this point as B, this point as C, another point as D, another point I'll take as E, another point I'll take as F. At point A I have given charge plus Q, at a point B I have given a charge plus Q, at a point C I have given a charge plus q at point D. I have given a charge minus q at point E. I have given a charge plus q at point F. I have given a charge plus q. I want the same question. Find the magnitude of electric field intensity at the point of intersection of the diagonals. Try this at home and let me know. Let me draw the diagonals here. A to D is 1. C to F is 1, B to D is this. At this point, what we have to assume? We have to assume a small positive test charge plus Q naught. Let me represent this point as well. Okay, try this. I've changed a slight variation I've given. What is it? Yeah, at point D I have replaced plus Q with minus Q. Try this. I can give you one more question I can also give, but later I'll give you. But try this. Okay, at point D I have given you minus Q in place of plus Q. That's it. Okay. Oh, written. Yeah. So let me wind up the class for today. Thank you.